Hello, everyone, and welcome back. In today's episode, we are going to be talking about differential equations and what it means to solve a differential equation and what it means to have a solution to a differential equation. So, to begin with, let's remember back from algebra what it meant to just solve an equation, period. A solution to an equation was just a value that you could plug into the equation and get a true statement from that. For example, if I was dealing with the equation, 2x is equal to 4, or I should say 2x is equal to 6, then I would say that x equals 3 is a solution to this equation because if I plug in x equals 3 to this equation, then I get a true statement. By contrast, if I plugged a different value into this equation, if I plugged in something like x equals 1, then plugging in x equals 1 would give me 2 equals 6, which is definitely not true. So x equals 1 would not be a solution to this equation. So that's all a solution to an equation is, just something that you plug into the equation and you get a true statement resulting from that. And it's exactly the same with differential equations. A differential equation, a solution to a differential equation is just a function that makes the differential equation true when you plug that function in. So, for example, suppose I gave us the differential equation, I want y prime to be equal to 2 copies of the original function y. I claim that the function y equals 2x is a solution to this differential equation. And the way that I would prove that my claim is true is I would say, okay, if y is equal to e to the 2x, then y prime by chain rule is equal to 2e to the 2x. And if I plug both of those results into my equation, then the left side becomes 2e to the 2x, the right side becomes 2e to the 2x, and those are the same function. So this statement is true. Yes, 2e to the 2x is equal to 2e to the 2x. No problem. Solution. A solution to a differential equation is just a function that makes that equation true. Now, when you're in algebra, you may hear this verb, this word solve, solve this equation. And let's remember from algebra that when someone asks you to solve an equation, they are asking you to find, or at least describe, all of the solutions to that equation. So for example, in algebra, if somebody said solve the equation x minus 3, x minus 1 equals 0, then my answer to that would be there are two solutions to this equation. X could either be equal to 3 or x could be equal to 1. This would be my response to the instruction to solve this equation because here I have listed all the solutions. I have listed all the values of x that make this equation true. Similarly, if someone ever asks you to solve a differential equation, they're asking you as well to find or describe all of the solutions. to find or describe all of the functions that make that differential equation true. Now, in algebra, solving equations can be pretty hard most of the time, right? There are only a couple of varieties of algebraic equation that were possible to solve by hand and get an exact result. You could solve linear equations, you could solve quadratic equations, and a couple of others, but most equations were not possible to solve by hand. For example, here, if someone says solve the equation 3 times x to the 5th power minus x minus 2 equals 0, I don't know about you, but I am not aware of any way to solve this equation manually by hand. I am not able to do that because this equation is too complicated. However, even though it is usually very difficult to solve equations, it is always easy to take a single value and check to see if that single value is a solution to an equation. Because if I'm in a scenario like this one, where someone says, I'm thinking about specifically x equals 1, could you check and see, is x equals 1 a solution to this equation? You can answer that question. Even though you cannot solve the equation yourself, you can answer this question just by plugging in the value to the equation and checking to see if the equation is true or not. Plug in x equals 1, plug in x equals 1, plug in x equals 1, and the left-hand side and the right-hand side both simplified to 0. So yes, 0 is equal to 0, and from that I can immediately conclude that x equals 1 is a solution to this equation. I can make that conclusion even though I was not able to solve the equation myself. And as well, if someone said, hey, actually, I'm thinking about x equals minus 3, is x equals minus 3 a solution to that equation? Again, I can answer this question even though the equation is too difficult for me to solve. I can answer that question just by plugging in this one specific value. And if I plug that in, 3 times negative 3 to the power 5 minus negative 3 minus 2, that one is definitely not equal to 0. So this equation is false. And from that, I can conclude that x equals 3 is definitely not a solution. I was able to do that, and I was able to answer that question, even though the equation was too hard and too complicated for me to solve. Now, this is the situation in algebra, and in differential equations, it's exactly the same. The vast majority of differential equations are too difficult to solve yourself. Even after you finish and graduate and pass differential equations, the math class, there will still be a ton of differential equations that are too difficult to solve. For example, as of this moment, standing right here, right now, if someone said solve y double prime minus 7 copies of y single prime plus 12 copies of the original function, I want all of that to cancel out and become 0. I do not think that most of you will be able to solve this equation manually yourself. I do not think that most of you have learned the method to solve this equation yet yourself. However, even though this equation is too difficult to solve, it is possible. It is always possible to check to see if a single particular function makes the equation true or not. For example, someone says to me, I'm thinking specifically of the function y is equal to 3x. Is this function a solution to this differential equation or not? Just like in algebra, I can check to see if this one specific function is a solution simply by taking that function and plugging it into the equation and checking to see if the result is true or false. So, in this situation, my y single prime would be 3e to the 3x. My y double prime would be 9e to the 3x. And if I plug all of that information into my differential equation, let's see what happens. In the front, I have 9e to the 3x. Then I have negative 7 copies of 3e to the 3x. And then in the back, I have 12 copies of the original y, e to the 3x, and that equals 0. And if I simplify that, I get 9 copies of the exponential minus 21 copies of the exponential plus 12 copies of the exponential. And in total, I have positive 21 and negative 21 copies of that exponential. So the whole left side cancels out, and I'm left with 0, exactly 0 on the left, and 0 as well on the right. And so because this equation is true, I can conclude that yes, this one particular function is a solution to this differential equation. I was able to make that conclusion even though I could not solve the equation myself. Likewise, if someone gave me a different function, y equals x squared, I can also check to see if this one function is a solution to the differential equation just by plugging that one function into the equation to see if I get a true statement or a false statement. So if I take y single prime, for this quadratic function, the first derivative will be linear, y double prime will be constant, and if I plug that information into my differential equation, I get 2 for y double prime minus 7 copies of 2x plus 12 copies of x squared. Is that the same thing as 0 on the right side? Now, this is not asking us to find a specific value of x that will satisfy this equation. This is asking, is this the 0 function? This is asking, does this completely cancel and vanish? And the same way that in the previous exercise, all of these terms completely canceled and completely vanished, leaving me with just 0 on the left side. In this case, I can see, no, there's not going to be any cancellation. There's not going to be any combination and vanishing. I'm not going to get something on the left side that is exactly equal to 0 all the time. And because of that, this equation is not true. The expression on the left is not the same thing as 0 all the time. So I would conclude that y equals x squared is not a function that makes this equation true. I would conclude that y equals x squared is not a solution to this equation. Okay, so I want you to keep that in mind as we go through the next several days of class. Most differential equations cannot be solved. in the same way that most algebraic equations cannot be solved. However, even if the equation cannot be solved, it is always possible and easy to check if a single value or a single function makes the equation true. Literally just plug that function into the equation, just plug it in and see if the result is a true statement or if it is a false statement. That's all you have to do, okay? Okay, so now that we have figured out the difference between solving an equation and checking to see if a single given function is a solution, I want to introduce you to one very specific variety of differential equation that we actually can solve right now just using the integration techniques that we've learned so far in this class. And the specific variety of differential equation that we can solve right now is an equation of the following format. An equation of the form y prime on one side of the equation, and on the right side of the equation we have an expression containing only the input variable. If I have a differential equation that looks like this, then I can find the functions that make this equation true simply by using a basic integration. And let me show you what I mean. Someone says, I'm thinking about a function called y, and I want y to have the following property. I want y to have the property that if you take its derivative, the result is equal to 2x cubed plus 4 e to the 4x plus cosine of 3x. So notice that this equation falls exactly into this category and format because I have y prime by itself on the left and I have an expression containing only the input variable on the right. I do not have any other y's or y primes over here on the right side. So this is falling exactly into this format. If you have a function's derivative and you want to know what the original function is doing, then the indefinite integral is absolutely perfect for that purpose. Because the indefinite integral is telling you all of the functions in the world that have this as that function's derivative. So the indefinite integral is the tool that I will use to help solve equations of this format. Y is equal to just the integral of the right-hand side with respect to x. So using power rule and chain rule, and making sure to remember my plus c, I am telling the reader that all the functions that make this equation true have this format. All the functions that satisfy this given equation have the format y equals 1/2 x to the 4th power plus 1/4 e to the 4x plus 1/3 sine of 3x plus some constant in the back. This is my description. This is my description of all the functions that make the equation true. This is my description of all the solutions to that equation. In this case, I was able to find it just using an indefinite integral. Let's do another example. Here I'm given the differential equation y prime equals 4 divided by t squared plus 1 over t plus 2. Solve this equation. So in other words, find or describe all of the functions that make this equation satisfied. So I observe that this equation is in precisely the correct format to use this idea, to use simple integration and say, okay, if I'm given information about y prime is equal to this formula, and on the right I have only input variables, in this case only t's, then the indefinite integral is perfectly designed to tell me all the functions whose derivative is equal to this. So I will take the indefinite integral of this expression on the right side, and I get 4 times arctan of t plus natural log of absolute value of t plus 2t plus some constant in the back. This describes the format of all the functions which make this differential equation true. So this would be my response to the ask, solve this differential equation. Now, to show you an example of a differential equation where this method could not be applied, I will give you, for example, y prime is equal to x times y. Here, I'm asking for a function where if you take the derivative of the function, the result has an extra copy of x compared to what you had originally. This would not be a differential equation that I could solve using a simple indefinite integral, because this differential equation is not of the correct format, where I just have y prime equaling expression that has only inputs in it. The y prime in this equation is equal to an expression that contains both inputs and outputs. And because of that, I would need a different technique and a different method to help us to solve an equation that looks like this one. And so that is what we are going to be learning how to do in episode 3 of this season. We are going to learn a technique that can be used to solve equations of this kind of format. And then as you go into the math class called differential equations, you're going to learn lots of additional methods to solve lots of additional varieties of differential equations in that class.